All right, so our next speaker is Chengsong Zhu, who is also coming from the University of Arkansas, and we'll look at some interesting other phases in bismuth ferrite.
Okay, thank you. Hello, everyone. First, I would like to, I'm Chengsong Zhu from University of Arkansas as a postdoc of Laurent Blaise. First, let me thank the organizer to give me this opportunity to present my work, and also thanks to the university and the supporters. Today I'm going to talk about the first principle prediction of multiferric hexagonal P63CM and hexagonal-like P1 phases in the epitaxial 111 BFO films. First, I will go through the rareness of multiferrics and quickly look at the two typical ones, bismuth ferrite and yttrium manganese, and then we will look at the epitaxial strain engineering. After the methods, we will look at the predicted phases in the order of increasing epitaxial, tensile epitaxial strain, and we will also have a conclusion. First, we know that the bismuth ferrite is well known for as the first room temperature multiferrics. It has a very strong polarization due to the large displacement of A-site bismuth and also its lone pair. And also the antiferromagnetism GTAP originates from the B-site iron. There is a relatively weak coupling between the two quantities because they are from different sublattices. Another example of a multiferric is the yttrium manganese. It is known for improper ferroelectricity, where the polarization is induced by the primary order parameter K3 mode, the tilting mode, and also the non-collinear antiferromagnetism from the geometrically frustrated antiferromagnetism. The coupling between the polarization and the magnetism is a little bit stronger. The two quantities are mediated by the K3 model. So we want to, we are talking about this because we want to deliver the message that the multiferrics are quite rare, and one useful method is the epitaxial strain engineering to create new multiferric phases. For example, when using the strong comparative epitaxial strain, the T phase can be generated, and the spin orbit magneto-electric coupling can be very strong here, and also for rare earth manganese, rare earth ferrites in the hexagonal phase, the large tensile epitaxial strain can also generate the yttrium manganese type hexagonal structure. So the question is, what about the BFO if it is pulsed on the 111 substrate? Will it have the hexagonal phase, or will the lone pair of bismuth ferrite play a role in increasing the polarization? So we are using those methods. First, the DFT calculations. I will just pass this, and the genetic algorithm combined with soft mode analysis to predict new phase, and also for the magnetic structure, we use the DFT to generate exchange parameters and then put into Monte Carlo and see the ground state. First, let's look at the perovskite phases. At zero strain, since it's the 111 substrate, it's the R3. No wonder it's R3, R3C, yeah. And then when it goes toward the tensile side, it first becomes to CC phase and then CC2. Those phases looks like this. As we can see, the epitaxial strain is quite large. Then Next, at even larger in-plane lattice constant, we notice that the hexagonal P63 CM phase becomes the ground state. And you may be surprised that this epitaxial strain is like more than 10%. But you may also notice that the local minimum is out of the curve of perovskite. So we think if this matter stable phase is really synthesized experimentally, there should be no strain effect here. And yeah, we also look at the paraelectric P-3C1 phase. It is always 15 millieV per formula unit higher than the polar P63CM phase. We now look at the polarization of this polar phase. As we can see, when the in-plane lattice constant increases, the polarization increases. We should note that for this phase, the polarization is pure along the C direction. It increased from this in-plane lattice constant for like 6 millicoulomb per square centimeter to this side. It's a 9 or almost 10. It's increased almost 60%. This is pretty novel because, according to our knowledge, normally when you increase the in-plane lattice constant, the polarization, the outer plane polarization should decrease. But here it is increased. And also for the yttrium manganite type hexagonal structures, it is also like this. The polar mode decreases when the in-plane lattice constant increases. So similarly to this kind of analysis, we also look at the modes, the phonon modes. When increasing the in-plane lattice constant, the primary K3 mode decreases, while the polar mode, the gamma-2 minus polar mode, increases. It's different from here. So yeah, this might be the direct reason for the increasing of the polarization. So what's behind that? Let's look at the energy landscape of the K3 and gamma-2 minus mode. At small in-plane lattice constant, the K3 has a double well. Means that this is the primary phonon mode, which is also the driving force of this phase transition. While the polar mode is a single well. That means the polar mode is induced by the K3 mode. Well, when the epitaxial strain becomes larger, we can notice that first the double well of the K3 mode becomes shallow, and then the gamma mode, the bottom of the single well first becomes flight, and then the double well emerges. So that means when the tensile epitaxial strain becomes larger, the proper component gradually come into play. Yeah, that's quite different and never reported in the yttrium manganite type hexagonal phases. And also for the magnetism, we consider the 4 typical non-collinear magnetic configurations, and the ground state at smaller in-plane lattice constant has the gamma-2 configuration and allows for the canted weak ferromagnetism. Then at even larger in-plane lattice constant, we notice there is another phase here. Again, I should stress that the local minimum is out of those curves. So if, again, this phase can be stabilized, there should be no strain here. The phase looks like this. It's pretty much looks the same with the hexagonal phase, and it is dynamically stable. Then we compare the structure between the P63CM and the P1 phase. We already noticed that the layered structure has been maintained. That means for the bismuth layer, the 1 up, 2 down, or 1 down, 2 up, it is maintained, and it contributes to the polarization, outer plane polarization. The major differences comes from the in-plane displacement. We can notice that in this hexagonal phase, the iron stay at the one-third positions ideally. While in this phase, we can notice that the iron and the oxygen, they break bond and they move against each other and then rebound at another direction. Here we mark those bonds as a specific iron-oxygen bond, since it will be related to the magnetism and the polarization closely. And also we look at the lattice constant. For the outplane lattice constant C, those two red dots are for hexagonal structure, and the green ones are for the hexagonal, the P1 phase. They are quite continuously. And since it is the thin film, we confine the gamma angle to be 120 degree. And for alpha and beta angles, they are quite close to 90 degree. So we call it the hexagon-like P1 phase to distinguish with the perovskite P1 phase. This phase has a quite novel polarization. Yeah, we know it has outer plane up and down polarization, but here we also notice that since one of the iron-oxygen bond will break, it has three choices. Each bond breaking can lead to a different in-plane polarization state. So totally there are 6-fold degeneracy of polarization in this P1 phase. And also for the polarization, besides the outer plane one, there is even larger in-plane one emerges, and resulting a quite large total polarization, which is almost twice of the 8 in the hexagonal phase. For the magnetism, we calculated the iron-iron exchange coupling, which is all the iron-oxygen-iron coupling. It is found that they are all antiferromagnetically coupled. And the more this angle is close to 180 degrees, the stronger is G. The most interesting is that the specific structure and the antiferromagnetic coupling results in a spiral magnetic ground state. This is a period of 9 unit cells. And if we look at the same site in each unit cell, we can find this is a spiral structure. And we need to pay attention that this spiral structure is totally different from the DM interaction-induced spiral structure. It is purely the frustration effect. Because I found that since it has a period of 9, each neighboring spin vector has an angle of 60 degrees. And we also find that the propagation direction of this of the spiral structure has a very close relation with the specific iron-oxygen bond. They always form a 6-degree angle with each other. Then we change the epitaxial strain and see how the exchange coupling changes. And then put them into the Monte Carlo simulations. We find that when we change the epitaxial strain, the exchange coupling changes, and then also the period of the spiral structure also changes. Okay. To conclude, we focus on the 111 BFO films, and then besides the perovskite, we found two hexagonal or hexagonal-like faces. They have quite novel magnetic and electrical properties. Okay. Thank you.
All right, any questions for our speaker? I'll get us started. As an experimentalist, I pretty much know the substrates we normally use, but to get out to those strain states, did you guys actually look and see if there are good materials?
I know your point, and that's why I'm always stressing on there should be no strain effect at this local minimum and this local minimum.
Yeah.
At another side, to stand on your point, those faces, the hexagonal one and hexagonal-like one, are highly matter stable. It's very hard to experimentally stabilize them, so we are trying to use a different method to lower the energy of these two faces. I mean, to lower those two curves toward this direction.
Yeah, I mean, I see the analogy with the compressive strain for the tetragonal-like phase as well, right? So once you get to that new energy minima, you can lock into it. I just don't, are there substrates that you have in mind that would work in this ballpark? Like, what are they?
You mean those substrates?
Those are the ones right there. Oh, okay, I see.
Yeah,
I gotcha.
Yeah, I suggested the
Awesome.
substrates.
Yeah, sorry.
Those ones, and for hexagonal phase.
Oh, okay.
Yeah, this one.
Great. Okay, great.
So have you thought at all about, the chemistry of this system and whether or not there are stable, vacancy ordering states here nearby when you try to make this? So for example, does this even, this is a very large energy change from the perovskite, right? So do you start forming oxygen vacancies? Do you start forming mixed valence on the iron site? What happens? Have you thought about that at all?
Shortly, no.
Thank you.
Putting the stability concerns aside, we can just look at it as a model system for interesting frustrated magnetism. Are there other ferrites, iron-containing systems, that have similar frustrated magnetic order? And can you compare how the magnetism here would relate to the magnetism in some ferrites? Because I've seen similar frustrated magnetic order in other transition metal systems.
To me, I didn't notice other system have the similar frustrated magnetic structure.
To me, it's somewhat reminiscent of the manganites. And of course, those occur closer to equilibrium lattice constants. But you may find some interesting magnetic analogies where you could learn about the energy magnetism relationships and see if they still hold for this interesting metastable ferrite.
Okay, I think I can talk further with you. But I can let you know that since we are talking about bismuth ferrite, if we replace the ferrite to a manganite, the phase diagram looks quite similar. It can also be stabilized in manganite, the two phases.
Any other questions? All right, let's thank our speaker and all the speakers of this session.
Thank you.